Hello, everyone, and welcome to Precalculus. This is the start of Chapter 5, Section 5.1, Using Fundamental Identities. We actually learned a lot of fundamental identities in Chapter 4, but we're going to learn 3 new ones today. The first of which is that sine of negative u is equal to negative sine of u. Now, if you understand why that's true, it'll be much easier for you. So I'm going to take a minute and explain it. Let's say that you had sine of pi fourths. Hopefully you know from looking on your chart or because you have it memorized that it's the square root of 2 over 2. Remember, that means it's the ratio of the opposite to the hypotenuse. Now, let's say I wanted to know sine of negative pi fourths. Hopefully your strategy would be to say that the reference angle is pi fourths, so the answer is still square root of 2 over 2, and then you would determine the quadrant. Since negative pi fourths is in quadrant 4, you would decide that because of forecast, sine is negative in quadrant 4. And there you have it. You can see it's exactly like they said. Sine of negative u is equal to negative sine of u. So if that made some sense to you, can you figure out what the rule is going to be for cosine? So for cosine, let's do cosine of pi thirds just to switch it up. Cosine of pi thirds is 1/2, which means that if I'm at pi thirds, this is a ratio of 1 to 2 for the angle pi thirds. If I want to know the cosine of negative pi thirds, the reference angle is still pi thirds, so the main ratio is still 1/2, but you would have to determine the sine. Well, since negative pi thirds is in quadrant 4, but cosine is positive in quadrant 4, the answer is still going to be 1/2, which means that this rule is that cosine of negative u is the same as cosine of u. If you still haven't tried one on your own, you should really try tangent of negative u. So let's do one more, not cosine. So tangent of, let's do pi 6, we haven't done that one, is the square root of 3 over 3. If I asked you for tangent of negative pi 6, then the reference angle would be pi 6, so the ratio would be the same. And negative pi 6 is in quadrant 4, and in quadrant 4, tangent is negative, which means that tangent of negative u is equal to negative tangent of u. All right, so we'll be using those 3 rules. You might want to put them onto your appendix. But to start out, we're actually going to do something really similar to what we did in Chapter 4, and that is finding the values of all 6 trigonometric functions. So for me, my 2 steps are always step 1, draw the triangle, and step 2, determine the quadrant. You need the quadrant so that you can figure out if things are positive or negative to determine the sign. So to draw the triangle, secant is hypotenuse over adjacent, and my quadrant, using forecast, since secant is negative and secant and cosine go together, I must be looking at either quadrant 2 or 3. That's where cosine and secant are negative. But it says tangent is greater than 0, which means that tangent is positive. So now I know I'm looking at quadrant 3. That's going to come into play when I do all my trig functions. So sine of theta, which is going to go with cosecant of theta, cosine of theta, which is going to go with secant, and tangent of theta, which will go with cotangent. So first I need to finish my triangle. 2 squared plus, let's just call that b. b squared is equal to 3 squared. b squared is equal to 9 minus 4 is 5. b is the square root of 5. So sine, opposite, over hypotenuse. Cosine, adjacent over hypotenuse. And tangent, opposite, over adjacent. But again, step 2, you have to use those signs. So since I'm in quadrant 3, sine will be negative, cosine will be negative, and tangent will be positive. To find these three, you just need to flip them because cosecant is the flip, the reciprocal of sine. So negative 3 over the square root of 5, which if you rationalize the denominator is negative 3 square roots of 5 over 5. Secant they already gave us, but this kind of confirms that we did it correctly. And then cotangent will be 2 over the square root of 5, which is 2 square roots of 5 over 5. Introducing a new Greek letter. This is the Greek letter phi, for those of you that are going off to college and are going to see lots of fraternities and sororities. So again, first step, draw the triangle. So cotangent is adjacent over opposite. And then to get my third side there, 3 squared plus 1 squared is hypotenuse squared. So the hypotenuse is the square root of 10. Notice I didn't even need this to make my triangle. Remember that when they give two trig functions, just use the second one for the forecast, okay? Don't even try to put it on the triangle, especially if they've already rationalized the denominator. This actually came from 1 over the square root of 10, opposite over hypotenuse. But when they put it in this format, it's hard to make it fit onto your triangle. So I am going to look at my forecast. So since cotangent is negative, cotangent goes with tangent, then I must be in either quadrant 2 or 4. But since sine is positive, now I know I'm in quadrant 2. So sine of phi is equal to the square root of 10 over 10. That was given. And then cosecant of phi must be the flip. And this is also where it's really nice not to have it rationalized because I can flip it easier. Cosine of phi is adjacent over hypotenuse, 3 over the square root of 10, which I have to convert to 3 square roots of 10 over 10. And secant of phi is the reciprocal, so square root of 10 over 3. Tangent of phi is opposite over adjacent, 1/3, and then cotangent of phi is adjacent over opposite, so 3. I go back and I put in my signs since I'm in quadrant 2. These are positive, these are negative, and these are negative in quadrant 2. For number 3, they used one of those identities that we learned right at the beginning of the video, and I personally am going to change it. If sine of negative alpha is negative 1/3, then sine of alpha must be 1/3. That would be so much easier to work with. So the first thing I would do is use that rule to convert it. So I am going to do this one a slightly different way so that you guys can decide what's easiest for you. Instead of drawing just any triangle and then doing forecast, I'm going to combine these two steps and do the forecast at the same time that I draw the triangle. So, meaning I know that sine is positive, so I must be in 1 or 2, and tangent is negative, so I must be in 2. So I'm actually going to draw my triangle in 2. So it's 1 opposite over hypotenuse is 3. And then 1 squared plus b squared is equal to 3 squared. B squared is equal to 9 minus 1 is 8, which is 2 square roots of 2. And people that do it this way like to label what's positive and negative. The 1 is positive because it's going up, but the 2 square roots of 2 is negative because it's on the left side of the y-axis. Then people that take the time to draw in the right quadrant, when they go to do their answers, the sign, the negative, like the, not S-I-N, S-I-G-N, the sign, positive, negative, is built right in. So sine is going to be 1/3, which means that cosecant is equal to 3 over 1. We'll just write 3. And then cosine is going to be adjacent over hypotenuse, and secant is going to be hypotenuse over adjacent. you do need to rationalize that denominator by multiplying the top and the bottom by the square root of 2. And I actually will move the negative to the top as well. 3 square roots of 2 over 4. And finally, tangent, which I realize is given, but let's use our triangle because then I can show you that it's a good way to check that it matches. So when I rationalize the denominator, I get, and again, bring the negative to the top, the square root of 2 over 4, which does match, so I feel very confident that I did everything right. And cotangent, which is adjacent, over opposite, which is just 1. Next one. Tangent of theta is undefined. So there's a bunch of ways to think about that. Personally, I would use the graph. Tangent looks like this, which means at pi halves, and then at all the pi halves after that, 3 pi halves, negative pi halves, there's an asymptote there. That's where it's undefined. So on the unit circle, that would be pi halves and 3 pi halves. Another way to think about it is that since tangent is sine over cosine, whenever cosine is equal to 0, that's when tangent is going to be undefined. So cosine is equal to 0 at, again, pi halves, 3 pi halves, 5 pi halves. And you can picture the graph this way. Starts at 1, ends at 1, and where is it at 0? At pi halves and 3 pi halves. But then the second piece to this puzzle is that sine of theta is greater than 0, which is a fancy way of saying positive. So sine, again, you can think about it graphically. Sine goes up to 1, down to negative 1. So sine is negative at 3 pi halves, but at pi halves, it's positive 1. So my answer is pi halves. Or maybe you just have it on the chart. You're looking at your chart and it says, when is tangent undefined? And that's great. You're welcome to just cross-reference on that. But the more ways you understand it, the better off you'll be. All right, so this gets into the crux of chapter 5. What we're going to be doing today is learning some strategies for the very challenging problems that we're going to do for the rest of the chapter. Section 5.1 is just a warm-up. So different strategies that you'll need to know for what we're going to call proving identities. The first one is being able to factor. So when I see secant squared x minus 1, you might think to yourself that it's just like x squared minus 1. If you can factor this, then you can factor secant. So this becomes secant of theta plus 1 times secant of theta minus 1. Again, if you have 4 tangents squared and that tangent is just really throwing you, then change it to an x squared and x. And then just factor this. So this is 4x and 3. Let's see, I want the 4 to be positive and the 3 to be the negative. Yeah, that works. So if you can factor it with x's, then you can factor it with tangent. And that strategy works for a lot of students. Now, of course, sometimes you don't have the same trig function. This is where another strategy comes in, which is change the form using the identities. So hopefully you have all your identities from chapter 4. When you see a cosecant squared, hopefully you're thinking about the Pythagorean identity, which says 1 plus cotangent squared is equal to cosecant squared. So I can replace this with 1 plus cotangent squared. Even if you're not required to memorize all the identities, you need to be intimately familiar with them in order to look at something like this and recognize when you need to use it. You can still look at your sheet to confirm, but if you don't have them mostly in your head, then it's going to be a struggle. So I am going to collect like terms here. Cotangent, oh, it's not theta. X, which is easier. X minus cotangent of x. And then because of that 1 and that negative 3, it's only minus 2. But then you can go back to strategy number 1, which is factoring, and if it helps you to write it as just x while you get your factoring down, that's always okay. So this becomes cotangent of x minus 2 times cotangent of x plus 1. Don't forget about factoring out. Just like you normally would, you can take things out. So sine of x comes out and we're left with cosine squared x, and we're left with 1 as a placeholder. Again, our strategy number 2, changing the form using identities. So another Pythagorean identity is that sine squared x plus cosine squared x is equal to 1. Now, I told you in chapter 4 you were welcome to have this written on your appendix in a whole bunch of different forms. 1 minus sine squared x is equal to cosine squared x. And none of them match what I need. So another choice, though, is to take ones that you have and make a replacement. If you don't have what you need on your list, then you could take the cosine and replace it with 1 minus sine squared x minus 1. And then 1 minus 1 cancel, and you get negative sine squared x, and that becomes negative sine cubed x. So that really simplified a lot. Could you have this identity on there? Sure, but it's unlikely that somebody would write it. It would require moving the sign to this side and then moving the 1 to this side. But if you would like to do that, to have every possible form of that same identity written on your appendix, then you are allowed to do that. Number 5. So this is actually going to bring us to another strategy, strategy number 3, which is to change everything to sines and cosines. So when I get something that I just look at it, I'm like, I don't even know where to start. I can't factor out. So change everything. This is a sine. Cotangent is the same as cosine over sine, and this is already a cosine. And at least now I can do something with it. I can change this to sine of t plus cosine squared t over sine of t. And now, I guess I won't keep writing on this paper, but we're on number 4 now. Strategy number 4, if you have 2 terms, get a common denominator. So a lot of times the way you simplify things is to make it into a single fraction. And I can do that by multiplying the top and the bottom by sine. Now this becomes sine squared t over sine of t plus cosine squared t over sine of t, which leads me to sine squared t plus cosine squared t all over, they have the same denominator, so I can put them together as a single fraction. And hopefully you're starting to recognize these, or at least saying to yourself, isn't that something? It is something. It is 1 is equal to sine squared plus cosine squared. Like I said, everything is going to be better if you learn all these identities. So it just asked you to simplify. This is considered pretty simplified, but you might also see the answer as cosecant. Either answer would be good. Okay, we're going to practice that strategy for that, getting a common denominator on this one, which is significantly harder. I'm going to multiply this one on the top and the bottom by 1 plus cosine of theta. And I'm going to multiply this one on the top and the bottom by sine of theta. Don't be lazy. Sometimes people only show it on just like in the middle like that. I will not give you credit for that. You must show it on the top and the bottom. So now I have sine squared theta over sine theta times 1 plus cosine of theta plus cosine of theta, I'm distributing here, plus cosine squared theta all over sine theta times 1 plus cosine of theta. They have a common denominator, so now I can write them as sine squared theta plus cosine of theta plus cosine squared theta all over sine of theta times 1 plus cosine of theta. And hopefully you're looking at this and recognizing sine squared plus cosine squared. So these two are going to allow me to write this as 1 plus cosine of theta over sine squared, or just sine theta plus 1 plus cosine of theta. And now since I have 1 plus cosine theta on the top and 1 plus cosine theta on the bottom, I can cancel, which doesn't just leave me sine. Remember, it's still in the denominator, so 1 over sine theta, which is a great answer, although some people prefer to write it as cosecant theta. Both answers are correct. So what we did just now is actually really similar to what we're about to do, except the directions specifically say rewrite the expression in non-fractional form, which means that if you had been doing this problem right here, then you couldn't have stopped at 1 over sine because it's a fraction. You would have had to change it to cosecant. So really, these next problems are just adding a step. So we're going to get more practice at getting a common denominator. Remember, do not be lazy. If you just do this, I will not give you credit for it. You're multiplying it to the top and to the bottom. That's what keeps the value the same, even though it's a little tedious to write. So this brings me to secant of x minus 1. Now be careful, I have to distribute this negative, and technically the 1, but it's just a 1. So minus secant of x minus 1. And now that they have a common denominator, I can make them all into one fraction. In the numerator, the secants cancel with each other, and so I just have minus 2. And in the denominator, I can simplify that because if I FOIL it out, I'll get secant squared x minus 1. And again, you really have to know these identities. When you see a 1 and a secant squared, you should be thinking to yourself, I bet that I can rearrange that somehow. And sure enough, if I replace the secant squared with 1 plus tangent squared, this is for the person that doesn't have them written 16 different ways so that you can just know what this is equal to. You can always just replace secant with 1 plus tangent squared, and then you will see that it's just tangent squared x. But remember, last step, they did say non-fractional form. So I need to move that to the numerator, and I can do that by using cotangent, which is its reciprocal function, cotangent squared x. Number 8. So this one has a denominator and this one doesn't. So I want to give it a denominator. And this one you don't have to write on the top and the bottom. Instead, you can just add a square because that's what's already up there. That will give me tangent squared x minus secant squared x. I can make it all into one fraction since I took the time to give them a common denominator. And again, you're probably looking at that saying, ooh, is that something? If you're not sure what it is, then just make a replacement. Tangent squared x minus, and secant is 1 plus tangent squared x, all over tangent of x. And then when I distribute the 1, you don't have to make it into a whole nother step. If you don't want to, you can just kind of write it above it. And then the tangent squared minus the tangent squared cancel, and I just get negative 1 over tangent of x. But again, last step, non-fractional form means I have to change it to negative cotangent because that's the reciprocal function for tangent. Number 9 leads us to yet another strategy that I'd like to tell you about. I think we're up to 5, and that is use the conjugate. You may remember that a conjugate is when you have the same terms, but it's a plus and a minus between them. So for this one, I see 1 plus sign, and I'm going to multiply the top and the bottom by the conjugate. See how the terms are the same, but they have different signs. The reason that I'm doing this is because 1 plus sign doesn't help me at all. But once I transfer it to 1 minus sine squared by foiling it out, it is going to help me. Because the identity that we're looking at is 1 is equal to sine squared x plus cosine squared x. This identity, 1 is equal to sine of x plus cosine of x, does not exist. Sometimes people really want it to exist because they just take the square root of each term, but that doesn't work. So you can only make changes if it's squared. So this method of multiplying by the conjugate is a great way to get it to have a squared, and now I can replace the 1 with sine squared x plus cosine of squared x minus sine squared x, and this denominator just becomes cosine squared x. Is it possible that you could go from here to here without showing this step? Absolutely. If you're going to do so many of these, you're going to start to recognize 1 minus sine squared is cosine squared, and that's tremendous if you're able to do that. So of course, how did that actually help me? This does not look any simpler than when we started, but that wasn't the goal. The goal was to make a non-fractional expression. So when you have a sign stuck to the 1, you can't just move that to the top and make it cosecant and then just leave the 1 on the bottom because it's attached by addition. But if you ever have sine as a product, then you can move it to the top and call it cosecant. Similarly, now that this is just a cosine on the bottom, now I can move it to the top. In this case, it becomes secant, and now I have gotten rid of my fraction. Let's practice another one with a conjugate. You might remember that tangent and secant are related when they're squared. So I see tangent and secant, but they're not squared. So I multiply by the conjugate. Make sure you do it to the top and the bottom. And that gives me 5 times tangent of x minus secant of x all over, I'm going to use FOIL, which will give me tangent squared x minus secant squared x. That might be one of the ways you have this rewritten, if you have it written, 5 different ways. But if not, there's never a problem with only having it written one way on your appendix and then just making a replacement. This is tangent squared x minus 1 plus tangent squared x, which if I distribute the negative means that my new denominator, let me just rewrite this numerator here, will be tangent squared x minus tangent squared x will just be a minus 1. Now most people, when they have a negative on the bottom, they just move it to the top. For example, if you had 3 over negative 4, most people would write that either as negative 3/4 or negative 3 over 4. This is very unusual. So we'll move that 5, we'll put that negative up at the top with the 5. And this is a great answer. However, if you're looking at answers and you don't see this one, is it possible that somebody distributed that negative or distributed the 5? Sure. If you distribute the negative, then the tangent becomes negative and the secant becomes positive. So you might see this. Don't let it throw you. If you stopped here, that's great. But if you see something else, just ask yourself, oh, does that mean the same thing? And they just wrote it differently. So next one, I see a cosecant and I see a 1, but hopefully you remember that the rule is 1 plus cotangent squared is cosecant squared. It doesn't work if it's not squared. But I can fix that by multiplying by the conjugate, which is cosecant of x minus 1. On the top, I'm not going to distribute that tangent, but on the bottom, I am going to FOIL out cosecant squared x minus 1, which is not how I have it. So it's possible that you've rewritten this a whole bunch of different ways, and then you don't have to make a replacement. You can just say, oh, I know that cosecant of x minus 1 is cotangent. What I don't want you to do is try and put this in there and then use arrows and stuff. Either you can state this as a fact, or you can do it the way we did it up here. But don't clutter your paper with these things. I want a nice fluid problem. Tangent squared x times cosecant of x minus 1. Again, our goal is to have a non-fractional expression. So I'm going to move the cotangent to the top. And because the reciprocal of cotangent is tangent, I'm going to have two more tangents up there. So I'm actually going to have tangent to the fourth x times cosecant of x minus 1. And that's number 11. So I realize these problems are really challenging. So what I've done on your upcoming quiz is I've made it a matching section. It's not as easy as it sounds. It doesn't mean that you're just going to be able to look at it and pick an answer. But what it means is once you simplify, at least if you don't see your answer there, you'll know that you didn't do it correctly. I'll show you what I mean. So this is going to be, I was about to write secant again, but I'm going to switch it to sines and cosines. Remember, that was one of our strategies. So 1 over cosine of x times cosine of x, which if you multiply straight across the top and straight across the bottom is cosine of x over cosine of x, which is 1. So I found an answer that's there. So I feel good about it. Number 2. Oh, so I see the squares, I see the cosecant. So I usually, for myself, would write down the rule, or for you, probably just looking at your appendix, and then make a replacement. So I can replace that cosecant with 1 plus cotangent squared x. And then that gives me cotangent squared x minus 1 minus cotangent squared x. These cancel and I just have negative 1. And again, the point of the matching is so you can say, oh good, that answer is there, and feel confident about it. It doesn't completely protect you from getting one wrong, but hopefully it'll help a little bit. Remember our strategy of changing everything to sines and cosines. Cosecant is 1 over sine. If I multiply straight across the top and straight across the bottom, those cancel. I won't even show that step. There's no reason not to do it right there. And that gives me 1 over cosine of x. I look at my answers and I don't see 1 over cosine of x, but it doesn't mean that I'm wrong. It means I might have to switch it. So another way to think of 1 over cosine of x is as secant of x, and that answer is there. On this one, I see a 1 and a squared, so you should be thinking about Pythagorean identities. This one is sine squared x plus cosine squared x is equal to 1. So 1 minus cosine, if I put that on the other side, is sine squared x. So that's one strategy, using the identities, and another strategy is changing everything to sines and cosines. I'm going to do both those strategies in the same problem, and then I have sine squared x over sine of x, which is just sine of x. I go back and look at my list, and it's letter F. So this brings back a rule we learned way back at the beginning of the video, which is that sine of negative x is the same as negative sine of x, but cosine of negative x is the same as positive cosine of x. And something we haven't used in a while is that tangent is sine over cosine. So this becomes negative tangent of x. Let's see if that's there or if I need to rewrite it. Nope, it is there. And if it hadn't been negative, I would have gone back and looked to see if I had made a mistake. Okay, what was that, E? I missed it. Yep, E. So there is another set of these for you to practice on your own. I would love for you to do that, but of course I am going to work them out for you. So the strategy I'm going to use here is the strategy of changing everything to sines and cosines. So 1 over cosine of x. And then I multiply straight across the top and straight across the bottom. And that's the same as tangent, which is b. A strategy I haven't used in a few minutes is factoring. Don't forget that strategy. So I'm going to change this to secant squared x plus tangent squared x times secant squared x minus tangent squared x. Remember, if you have trouble factoring, think of it as x to the fourth minus y to the fourth. You can factor that. So you can factor trig. Trig factoring and algebraic factoring is the same. And then I see a bunch of squares and secants and tans. So the other strategy is to think about your rule. 1 plus tangent squared x is equal to secant squared x. So I want the tangent and the secant on the same side. So I'm going to move the tangent over, and then I can say with confidence, oh, this is just equal to 1. But this is actually nothing. It looks like it's something, but it's not. When secant is being added to tangent, it actually doesn't simplify at all. Only secant minus tangent, as you can see from that. So I look to see if that's one of my answers, and it is. It's F. Oh, we get to use the same rule right away again. Secant squared x minus 1. That isn't the one that I came up with, but if I subtract 1 from both sides, then secant squared x minus 1 is tangent squared x. So this one's a little bit tricky. I'm going to show you 2 different ways to do it. One is to take the tangent and to change it to sine over cosine. And because it's squared, it becomes sine squared over cosine squared. But then I'd make a bigger line to show that's the top part of this fraction over this part of the fraction. Now, fraction over fraction is tricky. So I would flip the bottom one and multiply. Some of you might have learned it as keep. So I'm keeping this one the same. Changing from division to multiplication, and then flip. I just learned it as flip and multiply. And now my signs cancel, and I just get 1 over cosine squared x. I look to see, and it's not there, but I realize I can still make another change to it. So now I'm going to look to see if secant squared is there, which it is. Now, some people are really bad at the whole keep, change, flip. The fractions on top of fractions are just nightmarish. So instead, another alternative is to separate them. So move the tangent off to the side, and this is just times 1 over sine squared. People that do this are really successful. And this becomes sine squared over cosine squared times 1 over sine squared. So if that makes more sense to you, then by all means, do it that way. If that whole flip, multiply, keep, change, flip, whatever, doesn't make sense, then you can do it this way. Number 4. So once again, I'm going to take my 1 plus tangent squared x is equal to secant squared x. And you might have also had it written on your appendix as tangent squared is equal to secant squared x minus 1. So I can rewrite this as cosine squared x times tangent squared x. But then the next strategy that you want to use is changing everything to sines and cosines. And then these cancel, and I just get sine squared. I look to see if that's on my list, and it is. It's letter C. So letter C. Another thing is that sometimes people change it to sines and cosines right away. They don't like these as much, and that's fine. So when I distribute this, I get cosine squared times 1 over cosine squared, which is just 1, minus cosine squared. I look to see if that's on my list, and it's not. So you're still going to need the Pythagorean one, but you're going to need this one instead. Sine squared x plus cosine squared x. So I change the 1 to sine squared x plus cosine squared x minus the cosine squared x, and I end up with sine squared x. That just shows two extremely different paths to the same right answer. So not everybody's going to do these the same, and that's okay. Number 6, the strategy of changing everything to sines and cosines. The cosines cancel, and I get 1 over sine. I can look to see if that's on my list, but I recognize that if it's not, maybe cosecant is there. So I look, and cosecant is there. It's A. And last, so there's a couple different ways I could approach this. One is I could think, well, I could change everything to sines and cosines. It already is. Change everything to cosines by making my sine into 1 minus cosine squared x. That's a possibility. Then if I separate them, minus cosine squared x over cosine of x, then I get 1 over cosine of x minus cosine of x, which is secant of x minus cosine of x. And I look to see it's not there. So you might want to think about what's left. We've used B, F, and E, and from the next page we've already used C and A. But as you can see, that leaves me with D. How could I make sine tangent? Sine tangent. So I want to leave the sine but get rid of the cosine. So your alternative is to change this to sine of x over cosine of x. And now do you see it? That is tangent. So in just one step, that is tangent. And that's what we're going to start doing next class, is instead of just having you simplify as best you can, I'm going to give you the answer, and you're going to have to show the path that gets you there. Except that it won't just be one step. It'll be 5, 6, sometimes 10 steps long to get to that answer. But that's where this is heading. This is kind of the warm-up for this next section. All right, that's it. I hope you have a great day.